see you all here for this, our last lecture in our series this year on constructing the human being. And I'm very excited about our speaker this afternoon because he looks not so much at constructing the human being, but as repairing the human being. And he works on an issue, arthritis, that I work on myself, but in a very different capacity. So he's studying the tissue, the tissue in joints that allows them to function smoothly, and I tend to look at the joints in dead people after their joints long ago ceased to function, and the joints become very painful looking as dry tissue. And as an archaeologist and a physical anthropologist, I'm very interested in that. So the notion that this can be repaired, and the bony growths that tend to immobilize arthritic joints over the long term can be stopped in its tracks is an enormously exciting thing. So let me introduce to you our speaker today, Kyriacos Athanasiou. He is the Carl F. Hasselman Professor of Bioengineering here at Rice. He earned his MS, a degree that I have not in fact seen before, the PHM and the PhD at Columbia University. And he also holds appointments now in orthopedics and oral and maxillofacial surgery at the University of Texas. Currently, he is a visiting professor at the University of Thessaly, Greece. He's published close to 200 scientific articles and 28 patents. I was interested in his CV, but my printer ran out of paper before I got to 45 pages. He has also served as president of the Biomedical Engineering Society and is a fellow of the American Institute for Medical and Biological Engineering. In 2005, he was awarded the Van C. Moe Medal by the American Society of Mechanical Engineers. In addition to his academic interests, he has co-founded numerous bioengineering companies which have collectively brought to market 12 FDA-approved products. And so I will turn it over now to Kyriacos, who will be speaking on bioengineering towards mending the human being. Is arthritis indeed incurable?
Thank you very much. Thank you. Thank you. Thank you very much for the very nice introduction. Good afternoon, everybody. I truly appreciate the opportunity to be here today to show to you some of our most recent results related to articular cartilage. Well, you heard what the title of the presentation is. It is admittedly a little bit of a strange title, Bioengineering toward Mending the Human Being. Is arthritis indeed incurable? So let's see what prompted this title. When I was asked to present at this Scientia lecture series, the title of the series, of course, is Constructing the Human Being, and I was given this paragraph. And I read it again. I be honest with you, I couldn't really see where we could potentially fit in here. It says, the question, what is man, is the encompassing question for all philosophy. Individual humans are constructed through development, and the human species is constructed through evolution. Well, as a good scientist, as a good engineer, I said, well, let's start from the beginning. Let's figure out what this is all about. Let's see if we can fit in here. What is man? Well, let's do a little literature search. First thing that came up was Mark Twain's book, What is Man, 1906, where the old man and the young man are talking about what man might be. There are ideas of destiny, free will, but what caught my attention was the fact that the old man asserted that the human being is just a machine. I said, okay, we can fit in here. We're engineers, we can talk machines. So, well, however, let's make sure that we know what we're doing. Let's go back to the stalwarts of Western civilization, the people who came up with all of those wonderful things. And I went and found Sophocles, the famous playwright who wrote some of the most incredible tragedies. He wrote Oedipus Rex, Antigone, Ajax. And he said a human being is only breath and shadow. I said, okay, tissue engineering doesn't fit in here. Okay, let's keep digging. Next one was Protagoras, a sophist. He was famous for essentially saying that virtue, the good thing, is just getting ahead. And he said, man is the measure of all things. He said, okay, I'm going to give it one last try, and let's see if we can come up with anything. And I think the last definition, the last quote that I got was, again, from Sophocles, and I think he truly nailed it this time. I said, you know, we got the answer. He said, There are many dreadful things, but nothing is more dreadful than human beings. That's all right. I'm doing this, meanwhile, sitting here on this balcony in central Greece, in Pelion, Greece. This is my sabbatical year, as was mentioned. Pondering about all these cosmic questions here. And I said, okay, so what is human? What can we do here? Well, of course, when one talks about human and the definition, there are going to be elements of philosophy, religion, anthropology, but of course, biology and engineering. So we are bioengineers. We do biology and we do engineering. So I said, well, we're going to be just fine. So I don't know the answer. I really don't know what a human is. All I know, however, is what human does, and human gets arthritis. About 1 in 5 humans get arthritis. So undoubtedly, that is a very large number of people. That's a very significant problem because cartilage, as we will see in a little bit, is central in our ability to move, in our ability to walk, to talk, to eat. So motion is very, very important. So my group and I study how to get the human moving again, how to deal with those issues of arthritis, cartilage problems. So this is what we do. We study the musculoskeletal system. Going back to the old man, it's an intricate machine consisting of many parts that connect at various points that we call joints, right? All right. That we call joints. So we study the knee joint, study the hip, the elbow, the shoulder, the jaw joint, the hand joints, the foot joints. And we study, in particular, articular cartilage. There are 2 types of cartilage in the musculoskeletal system that we study. There is the hyaline, the glass-like cartilage, and this cartilage here. This is the thigh bone, and down here is the shin bone. And we see this white tissue that covers the end of the bone. We call this glass-like or hyaline cartilage. And then there is the other type of cartilage that we call fibrocartilage, and that is the knee meniscus. This structure shown here, that consists of 2 parts, these wedge-shaped structures that are made of this particular type of cartilage. The third type of cartilage that we study is another fibrocartilage, and that is the cartilage of the TMJ, the temporomandibular joint, the jaw joint. So again, hyaline cartilage and fibrocartilage. In particular, this jaw joint is an ill understood and studied joint. There's very little that we know about this joint. It is found right in front of our ear over here. And if we look at its makeup, we see that it's got essentially 3 main pieces. It's got this cranial bone up here, the glenoid fossa. It's got this bone here, the mandibular bone, and then this red tissue in the middle that we call the TMJ disc. Now, when these 2 bones move, that TMJ disc allows motion to take place. However, frequently, this TMJ disc bunches up in front of the bone, of the mandibular bone, and it impedes motion. High morbidity, very difficult problem. And the unfortunate thing is that the vast majority of the problems, close to 90% of the problems related to the TMJ, afflict young, premenopausal women. Ill understood joint, fibrocartilage. Let's see what we do in our group. So these are our areas of interest. We study hyaline articular cartilage in terms of regeneration or tissue engineering. And I'm using these terms here. There may be some nuances, some small differences. We use these terms interchangeably. So tissue engineering or regeneration of hyaline articular cartilage, the TMJ disc, the knee meniscus. And since, as we will see in a second, these tissues are biomechanical in nature. They're there to take force, to take stress, to allow for motion. We study the effects of biomechanical forces on them at both the tissue level as well as at the cell level. However, today, we will only concentrate on 4 points. First, we will differentiate between hyaline and fibrocartilage. We will then show 1 or 2 findings from our tissue engineering studies. Then we will concentrate mostly on new stuff that we're doing now in the group related to what we call the cartilage self-assembly process and alternate cell sources for tissue engineering cartilage. Incidentally, this is another picture from that balcony. Now you can see why I have difficulty concentrating at times. This is right here in this third finger sticking out here, this area here, this bay here, is where, according to mythology, as well as history, some people say, this is where Jason and the Argonauts set sail. So a perfect place to think about things and try to figure out what human beings may be. So articular cartilage. I said this is a mechanical tissue. It gets affected by mechanical forces. Well, because its functions are mechanical. It's there to allow for lubrication. So every time I walk, and my knee joint moves, the coefficient of friction is so small that it is much better than some of our best designed machines. And this is a joint that operates in this almost frictionless condition for 6, 7, 8 decades of life. So a pretty remarkable tissue. It allows for load transmission. So every time I walk and every time I run and every time I jump, I generate forces in my knee or my hip that are pretty large. We're talking about 10 to 15 megapascal of pressure, which if we put it in terms of pressure in our tires, if our tires have 30 PSI, say, we're applying 1,500 to 2,000 pounds per square inch in that joint every time we jump or every time we go up the stairs and all that. So a tissue that is exposed to significantly large stresses. So of course our motivation is that osteoarthritis, one form of arthritis alone, affects 20 million people in the US alone, costing a lot of money. And we note there are two types of osteoarthritis that we can speak of. There is the primary type, which is wear and tear. So I have the motion in my joints, and eventually with wear and tear, the cartilage begins to break down. Versus the secondary type, which can come about because of an injury. So I get a large force, and a large force may create an osteoarthritic phenomenon. For instance, one form of cartilage injury is motor vehicle accidents. So here's this knee right here, doesn't look very happy. When this knee hits the steering wheel or the dashboard, an impact load is created, and those impact loads may not cause visible damage to the tissue, but this damage eventually may lead to osteoarthritis. So here's our TMJ. Here is the knee meniscus structure. And here is a human hip joint where we see the highlight covering the ends of the bone. Now, what these three tissues have in common is the fact that they cannot mount an effective healing response when they get injured, say that motor vehicle accident that we spoke about, or early pathology, osteoarthritis, early osteoarthritis, or osteochondritis dissecans, or some other disease of cartilage. So I'm not going to get too much into the biochemistry of things, but I'm just going to tell you that these tissues consist of primarily three components. A lot of water. So these are highly hydrated tissues. About 75 to 85% is water. Lots of collagen. Hyaline cartilage is type 2 collagen. Fibrocartilage is primarily type 1 collagen. And this molecule here, this what we call glycosaminoglycan, or GAG, which is a molecule that plays a very significant role. It may be beyond the scope of our conversation today, but suffice it to say that when we look at whether we can make cartilage, we look at collagen, the type of it, and the GAG. Here, for instance, we see that if we stain this tissue with this appropriate stain, we see GAG stains red. So I'm looking for this red color, if you would. So let's compare the three tissues in terms of collagen and GAG. Hyaline cartilage is almost entirely type 2 collagen. The TMJ, on the other hand, is type 1 collagen. The knee meniscus, about 3/4 type 1, and 1/4 type 2. Let's look at the GAG. Hyaline cartilage has a lot of GAG. The other two do not. Usually, a tissue that has a high amount of glycosaminoglycan will be a tissue that can take compression, that is good in compression. Lo and behold, if we look at the compressive characteristics, we see that this hyaline tissue is a lot higher than either the knee meniscus or the TMJ disc, which means that in terms of tensile characteristics, meaning their ability to resist pull as opposed to push, compression, tension, pull, the tensile characteristics, hyaline cartilage is very low, unlike the TMJ disc and the knee meniscus. So we said that these three tissues cannot heal effectively. That may be due to the fact that cartilage is an avascular tissue. It doesn't have any blood supplies. If it doesn't have any blood supplies, it doesn't have any nutrients. It has a very small number of cells. The number of cells is so small that perhaps those cells are unable to communicate with each other and say, well, we have a problem. Let's try to repair it. So these are hallmarks of a tissue that is notorious to heal, unable to heal. So the healthy femoral head here, the glistening, smooth surface, becomes this, an osteoarthritic femoral head, where now this arrow here doesn't show me cartilage, it shows me bone. So I have exposed bone. Cartilage is completely gone. Not only that, these other arrows here show me pitting in that bone, an extremely painful, difficult situation. So, and I apologize for the graphic nature perhaps of the next one, but could do it quickly. In terms of the knee joint, we have the same problem, and in such a case, we need to go in there and we need to remove the cartilage and the bone, and we need to put in there a piece of metal and a piece of plastic. So there's got to be a better solution to that problem. There's got to be a solution in which we develop a biological substitute and go in there and replace that knee or that hip. So let's talk a little bit about tissue engineering. The two Argonauts here, right? This is the house up here, actually, where we're staying. So let's show just one or two results related to tissue engineering. This is the approach that we historically followed, and we still follow up to a certain degree in our laboratory. We take cells, we put them on scaffolds that degrade, that break down with time. Then we take these cell-seeded scaffolds and we expose them to different biochemicals that are called growth factors. And these biochemicals have the ability to turn various processes on. Perhaps it can make these cells produce tissue. Then we expose these things to biomechanical stimuli because, like I said, these are tissues that are biomechanical in nature. They respond to biomechanical forces. And the idea is to engineer, to make a piece of cartilage in the laboratory, what we call in vitro tissue engineering. These are pictures of some of the biomaterials that we have used. These are FDA-approved biomaterials. They're degradable. They're from the class of materials called polylactides, polyglycolides, basically polylactic acid, polyglycolic acid. And let's look at one result, for instance. If we take meniscus cells and put them on one of these materials, polyglycolic acid, a material that degrades very fast, and we examine different growth factors. I'm not going to bore you with the details, but there is one growth factor here, this TGF-beta 1, that seems to be head and shoulders above everybody else. Look where it is, look where the control is, in terms of making collagen, in terms of making GAG. So we can identify growth factors that have a profound effect on the ability of the tissues to make cartilage. Then we looked at meniscus cells placed on polylactic acid, a different biomaterial that degrades much more slowly. And again, we see with the growth factor, we get a lot more tissue than without it. As a matter of fact, if we measure these amounts, we see that everywhere where we have this T for TGF-beta, we see that we have almost a couple of orders of magnitude more tissue in terms of collagen and GAG than if we do not have that particular chemical, that particular growth factor. Some very exciting results are coming out right now in the lab from Deidre Jones in our group, where Deidre took TMJ disc cells and she tried to engineer the TMJ disc. Well, this is what we got. Nothing to write home about. These small pieces that make collagen but do not make any GAG. Well, what we did, we decided to go into the rib cartilage direction there, take some cells from rib cartilage, and then we tried to make the TMJ using rib cartilage. And lo and behold, we can make good, nice pieces that stain very well for collagen as well as glycosaminoglycan. So potentially, we're opening a new direction where we could be using cartilage from the rib, a little bit from the rib, to make the TMJ disc. Now, let's talk a little bit about cartilage self-assembly. This work is motivated by the currently applicable technique to make cartilage repair. This is a clinically usable and acceptable technique. It's called the Cardi procedure. Let us say that we have a defect in our joint, someplace here. Our friendly local orthopedic surgeon removes some pieces of cartilage from the periphery of the joint, sends them to a laboratory. They extract the cells out of there. Then they multiply those cells many times. They passage the cells, as they call them. So they remove them from one surface, place them on another, etc. So they passage the cells multiple times, maybe 5, 6 times. Then they go back a few weeks later, and they go into where the defect is. They cover this defect with a piece of periosteum, the thing that covers the bone here. We cover it up, and then they inject the cells inside that defect. So it's a technique that works admittedly quite well, but it hasn't really caught on. And the reason why it hasn't, in our opinion, is because of what we observe with these cells when we passage them. So if we take these cartilage cells and we passage them, remember I said they passage them a few times. If I passage them and then I measure the propensity of those cells to make tissue, what we call the gene expression, the propensity to make tissue, I see that immediately the cells, the gene expression for type 1 collagen shoots up very quickly. Remember, we do not want type 1, we want type 2. So type 1 goes up very high, type 2 drops very quickly. This superficial zone protein that is characteristic of articular cartilage is gone, and aggregation stays about constant. So a pretty significant result, as he points out, that these cells de-differentiate. They change character, they change personality after 1 or 2 passages. So basically, the cells that are going to put in that defect may not truly be cartilage cells anymore. Well, the question that we asked next was, well, is there a way that I can take now these cells that have de-differentiated, changed, and can I push them back into the right direction? Can I make them back, become like cartilage cells? And I apologize for this slide. Don't worry so much about what's in here. Just keep in mind the following. We used different surfaces where we took some proteins, we stuck them on the surfaces, and then we put those de-differentiated cells on the surfaces to see if they could receive some signals from those surfaces that could push them back into the cartilage direction. Well, collagen 2 was bad, caused further de-differentiation. But we discovered that aggregation, a surface made out of aggregation molecules, pushes the cells back into the cartilage phenotype. Very exciting result, and we will revisit this result in a few slides down the line. There's some very significant work in the group done by Dr. Jerry Hugh in the group when he was still a PhD student, where the objective was, we said, well, when we use these scaffolds break down. When they break down, they release things. Okay, they may be FDA approved, but they seem to interfere with certain processes. Is there a way I can make cartilage without using a scaffold? Well, I'm going to remove the suspense here. The answer is yes. So we decided to call this process a self-assembly process. And lo and behold, what Jerry showed was that we could take cells and we can help them through the process that we developed, assemble by themselves, and create cartilage that looks like this by 4 weeks, 8 weeks, and 12 weeks. So clearly, we're making what appears to be cartilage. It has the right dimensions. These are the dimensions of a defect that we have in a knee. So we are very excited about it, but is this cartilage indeed? And the answer is, yes, it is. So if I look at the stains, it stains this red color. It's GAG, it has a lot of GAG. It stains this brown color that in this case indicates type 2 collagen. So very excited about the fact that we can produce cartilage in a scaffold-less approach. We proceeded with this technique further, refining it, and work done by Chris Revel in the group, where now we can make these pieces of tissue, entire pieces of tissue, that have biomechanical properties, because the most difficult thing is to make something that's strong enough to take up the pressure that is on par with native tissue. And even more recent work done by Ben Elder in the group, where Ben can coax these cells to make tissue, creating these struts in collagen. So basically, he makes a tissue that's anisotropic, as we say. It's got properties that are much better in one particular direction, the direction where compression is going to come. And then a brand new result that's extremely exciting is that the effect of hydrostatic pressure on this process. So if we take these self-assembled constructs and we expose them to hydrostatic pressure, with this system here, we show that we get a mechanical modulus that it is much better than what we get. And you got to remember, in terms of mechanical properties, things don't change that easily. So we're very excited to see that we have a 2- or 3-fold increase in that compressive modulus. We can also make these tissues now to achieve thicknesses that can be as thick as the thickest human cartilage, which approaches 4 millimeters thick. This is a normal meniscus. This is what a knee meniscus looks like. Now we are tissue engineering the meniscus using co-cultures, combination of different cells. And what we can show is that we can, we're at the early stages, but we can make what appears to be the knee meniscus in vitro in the laboratory without using any scaffolds. We can give them characteristics, again, that are akin to the characteristics of the native meniscus. So for instance, we can make these tissue engineered constructs have collagen fibers arranged in this direction such that this meniscus structure here can take up those hoop stresses, as we call them, a type of stress that develops in the meniscus. That's what makes my meniscus strong enough to take all that biomechanical abuse every day, essentially. And the last result in this area here, we're very excited about this result because for the first time now, we're able to take molds. Parenthetically, let me indicate that the science that you see here is that of a New Zealand white rabbit. It's not the human. So we're not at that level yet. This is the New Zealand white rabbit here. So we can take that mold and we can, for the first time, make the entire distal femur. So this is the first time that something like this takes place, which bodes very well toward treatment of osteoarthritis, toward treatment of the entire cartilage surface. Because up to this point, we and everybody else talks about small local lesions in articular cartilage. Now we're talking about the possibility of resurfacing the whole distal femur. The last topic of the day is about alternate cell sources. Let me tell you what I mean by that. When we talk about tissue engineering of articular cartilage, I'm the first person to tell you that we do not have that much cartilage in us to take out and take cells out and try to do our maneuvers. I mean, where am I going to take the cartilage to fix things? So it would be ideal if we could identify another source that would allow us to obtain the large numbers of cells that we need. So the question that we asked is, can this self-assembly process be developed to engineer cartilage constructs without using cartilage cells? Specifically, can I use skin cells? And can I use human embryonic stem cells? Okay, human foreskin cells and cartilage, some incompatibility here. Let's see. Margaret French in our group, a few years back, took these human foreskin cells and placed them on the regular surface, and this is what they look like. This is the characteristic of a skin cell. It's a fibroblast. When she took those cells and placed them on aggrecan, remember a few slides ago I said aggrecan seemed to have some effect in pushing those cells back into their original character? When she placed those cells on aggrecan, those cells kind of rounded up, created little nodules, which 1 week later were expressing this red color Remember, it indicates gag. So skin cells seemed to be making a cartilage-specific protein. Well, since that work, we got inspired by that work, and outstanding work done by Daisy Deng in our group, where Daisy now took goat skin, pieces of skin from the goat. Then we developed an isolation process that allows us, out of all of these fibroblasts that we take from the dermis, isolate a small portion of those cells that are called DIAs. Dermis isolated aggrecan sensitive cells. So these are cells that are sensitive to aggrecan, that protein that I spoke about. Because when you place these cells on aggrecan, they seem to do strange things. What kind of strange things? Well, if I place these cells on my regular surface that I use in my tissue culture in the laboratory, well, they don't produce GAG. They don't produce collagen 2. However, if I place them on aggrecan in the lab, they bunch up over there, they create these nodules, they make GAG, and they make type 2 collagen. Well, pretty spectacular result, but this is two-dimensional. Okay, there's a difference between showing these things two-dimensionally and trying to make tissue that is three-dimensional in nature. Well, proceeded further, said, well, let's try to make tissue with this thing, if possible. First, as a control, we're gonna go to the goat, and we're gonna take cartilage from the goat, and using the self-assembly process like I described before, we can make pieces of cartilage, here they are, that stain red for GAG, they stain this brown color here for collagen 2, and no brown color here, no collagen 1. Okay, good. That's my positive control, so I can do that. If I take the skin cells from the dermis, however, they don't make any GAG, no collagen 2, and they make a lot of collagen 1. If we take the DIA cells and we try to tissue engineer cartilage, we see that we can produce tissue that stains red for GAG, stays this brown color here for collagen 2, and no stain for collagen 1. So it's a pretty spectacular result because it clearly indicates that we can take skin cells and then we can coax the skin cells into producing articular cartilage. This paper was published just a couple of months ago in Arthritis and Rheumatism. So I'm going to finish with talking about human embryonic stem cells. And of course, these are cells that elicit all kinds of reactions, positive, negative. I don't think there's anybody who has neutral reactions. So if one looks at a fertilized egg, 5 or 7 days later, we obtain what we call the blastocyst. Inside this blastocyst, there is a number of cells, the inner cell mass, that when those cells are isolated, in theory, these cells have the potential, the capacity of becoming any cell type of the body. Neurons, red blood cells, and in our case, chondrocytes. Now, let me throw a caveat over here. My arrows look nice and straight, but I don't want to give the impression that these are straightforward processes or that these processes have been established. It looks nice as a schematic. However, in our hands, we have been taking these human embryonic stem cells, and we have developed protocols that allow us to differentiate, basically to establish the arrow, this arrow here. We're trying to establish this arrow that comes down to the chondrocyte. So we have been obtaining this, what we call differentiated chondrocytes, basically chondro-induced human embryonic stem cells. And of course, the question is, can one use these cells to make tissue? And the preliminary answer is yes. We can make very nice pieces of cartilage from entirely a human embryonic stem cell source. Again, clearly, there's a lot of work to be done here, but it is very exciting that, that something like this can happen. This is excellent work done by Eugene Coy and Gwen Hoban in our group, and it really, really opens up an entirely new direction for us, as it truly suggests that we can get on this pathway and proceed with it. I think I've described to you today that there are a lot of achievements in tissue engineering that suggests that we might be able to treat articular cartilage afflictions. I said, we are identifying novel cell sources that we can use because there aren't that many cartilage cells available out there. We can use primary cells, cells that we take straight from the tissue, or cells that will passage. Remember, they get passage, they change their character, and perhaps we can get them back to where they were originally. We spoke about these Diaz cells. Those are skin-derived cells that have the capacity to be chondroinduced to become cartilage-like cells and make cartilage. And we spoke about human embryonic stem cells. I said there are certain biochemical signals that work wonders for some of these cells. Some growth factors, for instance, that have some unique properties. Although I didn't really spend a lot of time on biomechanical stimuli, I think I gave you some indication that hydrostatic pressure and perhaps direct compression have some important effects on these cells in helping these cells make better tissue. Then at the end, I spoke about cartilage self-assembly, which is a very exciting technique for us that allows us to do away with scaffolds altogether. I believe it was Socrates who said that I think he said, he who gets on top of the highest peak and exhibits hubris will be struck down by Zeus's thunderbolts. So I'm not going to get on the highest peak and exhibit hubris. However, I cannot help but be excited about where this work is moving. We envision a pathway in which we can take cells from the skin or cells from a stem cell bank, follow the established pathway that we're defining now to chondroinduce them, to make them like cartilage, such that we can make the tissue and replace not only focal lesions, but perhaps the entire joint. I should caution you, however, that this is really talking ahead. We're not in a position to do that yet, but we hope that that's where we're headed. So the question, is arthritis indeed incurable, that we posed at the beginning? I believe that today I'm showing you some suggestions, some evidence that bioengineering suggests that this may be a curable problem in the near future. My group has traditionally worked on what we call the translational aspect of research. Here at RISE, and before when I was at the University of Texas Health Science Center in San Antonio, my group has been developing things that find their way into becoming FDA-approved products. I founded or co-founded different companies, and among themselves, among the 5 of them, there are 13 FDA-approved products. So clearly the stuff that we describe here, we do work which may be quite basic in nature, but we always have an eye on seeing this work being translated into usability in our own lifetime. This is an old picture of the group. I've been on sabbatical this year, so I didn't have a newer picture to show, but I have specific pictures of the group. It goes without saying that the work that I presented here today is because of these individuals. We're very, very fortunate here at RISE to have individuals of this caliber, truly outstanding students who, of course, keep me on my toes, but they are the ones behind all of this work. And I would be remiss if I did not single out Dr. Jerry Hugh for all of the work that he's done here for us. Finally, we are grateful to our funding sources, in particular, our concurrent 3 R1s that we have from NIH, from NIAMS, NIDCR, and NIBIB. So with that, I'm going to have some pictures flashing up there, but I'll be more than happy to take any questions that you may have. Thank you for your attention.
Before you
Well, let me give you an idea. That first company that I listed there, Osteobiologics, I founded that company in 1993. A couple of patents that we came up with my group at that time. The first FDA-approved product was in 2003, so it was 10 years later. And the company was acquired just last year by Smith & Nephew. So it takes a very long time. When we were projecting how long it would take us, we said no more than 5 years. 5 years very easily became 10 years. And a lot of money, of course, too. So you know, there are so many unpredictabilities that come about when one tries to commercialize these things, I mean, through the FDA process. I would like to point out, of course, that I'm not part of the commercialization process. We do the work, proof of principle, get the patents, then those get licensed out, and then the companies run, you know, with what they have. But it usually takes absolutely no less than 5 years, probably takes more than 10 years.
Thank you. I have a question. Have you tried actually to incorporate any of the products that you created without scaffolding back to the defect in animals, or how do they behave?
I don't know the answer to that. That's an excellent question. So the question is, so if you tissue engineer a construct that is using a scaffoldless approach, how would it behave when you try to integrate it with the adjacent tissues? And I don't know the answer to that question. We haven't done any of the in vivo studies as of yet. I mean, clearly those are going to be the next steps. And we have some protocols in mind, but we haven't really shown that yet.
What's the possibility of injecting a massive chondro-induced cells into a joint?
So the question is, if I have a bunch of cells and I'm going to inject them straight into the joint, would they localize? Would they go and find the defect and attach and do what they know what to do best? Which I don't know if they know what to do best because they don't do it very well. But there are split opinions on that. There are a couple of studies that say that if you take stem cells and you inject them, mesenchymal stem cells, and you inject them, somehow those stem cells have the capacity and the capability of figuring out where the problem is, and they go there and they attach. But I would say that a plethora of other studies show that that may not be the case. So I do not believe that by injecting cells straight into the joint, those cells will figure out what they're supposed to do. Somebody needs to guide them a little bit more. Do you want to handle the questions, or do I?
Oh, please.
Okay.
So, what you could make a piece of cartilage to order?
I'm sorry?
You could make a piece of cartilage to order size.
Yeah.
How would it be attached?
I think that's the question is continuing on from the question that was asked before. So the question is, how does that tissue integrate? Okay. So if it is a small lesion that we're talking about, in the past with scaffold-based approaches, we can show that we can take the tissue-engineered cartilage and we can press fit it into the defect, and it stays in there so long that the defect is deep enough. And it can stay in. If it breaks through the bone, basically, you can press fit it and it stays in place. The question, however, is if we are talking about replacing the entire surface, how would we attach that? And there are techniques. I mean, we haven't done it yet, but there are techniques where one could potentially use biodegradable attachment, like screws or something of that sort, and basically put that like a baby's cap, straight onto the bone and attach it over there, and promote integration, if you would. But since we haven't done that, this is all speculation at this point. Yes, sir.
In the studies you've made, have you found any beneficial effects on cartilage by using glucosamine chondroitin?
We haven't studied. I guess you're referring to the supplementation with glucosamine and all the supplements that are out there. We haven't done it. We haven't examined it ourselves to know. Again, I have seen studies that say that there is an effect. As a matter of fact, I have some orthopedic surgeons friends. I'm not an orthopedic surgeon. I have some orthopedic surgeons friends who say, well, one of them in particular said, I'm such a skeptic, he said, but I had this individual who kept asking about these supplements, and I said, well, what the heck, just go ahead and try it. He said, I was surprised to tell you that individual improved significantly. So I said, are you still a skeptic? He said, well, I don't know how it works, but it seems to have an effect. However, I would say that scientifically speaking, it would be difficult to see how a supplement might be able to reach the area, the problematic area in the joint. Since, we take it, we eat that thing, right? To find itself, those macromolecules, not to be broken down and find themselves, how to for them to figure out how to get to the site of injury, I think that would be too tall of an order to ask them to do. So personally, I don't think that it does very much.
Currently, a lot of arthritis is treated with the Fosamax Actinol.
What?
Fosamax Actinol, and I have no idea how that works.
Neither do I. Yeah, I really don't know.
You mentioned mostly osteoarthritis, but does this have implications for other arthritis, like rheumatoid arthritis?
Well, the problem with rheumatoid arthritis is that it's more of a systemic type of a disease. I believe that the work that I'm describing here will have a lot of significance and will help in the direction of treating rheumatoid arthritis. But clearly we need to figure out how to stop it at the systemic level, so the body doesn't attack. We may be putting your cartilage, if it gets attacked again and gets destroyed again. This work will help with rheumatoid arthritis, but I don't think that it will be a straight, a treatment that it would work by itself.
What is Smith and Nephew doing with osteoarthritis? What are they doing with it?
That's a good question. I really don't know the corporate world's doings there. My understanding is, which is public information, of course, is that they're keeping it as such intact, and they just bring it under the general umbrella of Smith and Nephew, and they have a much better, more organized sales force to sell those products, basically. But they're keeping it intact.
Did they have a research and development department?
Smith and Nephew? Osteologics? Yes, they do.
If I wanted some cartilage later on, can I use anybody's T cells as stem cells, or do I have to use mine?
Very good question. Well, again, I'm not giving you any straight answers today, am I? Cartilage cells, cartilage is supposed to be, and I stress supposed to be, immunoprivileged. People say that you can take somebody else's cartilage and somebody else's cartilage cells, and if you put them, so I can take from your cartilage and put it in my joint, and there's not going to be a reaction because cartilage is supposed to be immunoprivileged. I really don't think so. I don't know. I don't think anybody knows. It's like, well, let's do it and let's see what happens. I believe there will be an immune response, undoubtedly. It may not be as vigorous as if one replaces a piece of bone with all the vascularity and all that, but nevertheless, I expect that there will be some immune response. One perhaps needs to be talking about antigen matching and things like that.
Can I ask a general question? Do you think there'll be a time when a person is born and they'll save the placenta and the umbilical and freeze it and keep it for later regeneration and stuff?
I think they're doing that already. Some places they're doing that, specifically for that, to save the stem cells and use them if need be at a later time.
Is there any work done on cartilage transplants?
Cartilage transplants from one location to the other, say?
Or like from a deceased person that
Yeah. Yes, there is so-called allotransplantation, transplantation of piece of cartilage, say, from a diseased individual. And and again, depends on what group does the work. There are studies, especially coming from a couple of groups in Canada, that report exceptional success using cartilage that comes from a cadaver, basically, fresh cadaver. There are other people who do not report as high of a success rate. Of course, there's always the danger of transmitting pathogens and other problems that we may not know what they are. But it is definitely a viable thing to do for some people. It is not a widely used process, however.
Can you say something about the nature of agrocans that has these magical properties?
Did I say magical?
Well, I said, I added that.
Well, I mean, agrocans sort of makes sense in the sense that when we look at what cartilage is made of, it's made of that stuff, all these macromolecules there, and it's made of collagen. And those macromolecules is like having a tree with all of its branches coming out, those stiff branches coming out, and those branches are negatively charged. Because they're negatively charged, they try to neutralize their charges. So they attract a lot of water. This interplay, I mean, I can spend 2 hours talking about that, but that interplay between the negative trying to neutralize those negative charges is what gives cartilage its mechanical characteristics. That ability to hold on to the water, because of these electrostatic forces, is what makes cartilage the tissue that it is, the stiff tissue that can, here's an avascular tissue that can withstand stresses and strains, 70, 80 years, right? So, and it is primarily due to the existence of those negative charges in those molecules in there. So now, our original idea was that, well, if we take these cells that changed character, if you would, and try to place them on proteins that come from the extracellular matrix of the tissue, perhaps those cells will recognize some signal from there and say, well, this looks good. I should go back to being a cartilage cell. Now, the exact mechanism of what that might be, we don't know. But that's the idea, that the cell will recognize basically that molecule, and some signaling mechanism will take place, a cascade of signals will take place that will convince those cells that it's a good place and they can do the right thing. I sound very philosophical, don't I? I mean, okay.
Is there one more? Should we take one more?
Sure.
Sort of a weird question. You said that when cells undergo the passage technique, they become differentiated, then you need to put them in an aggregate to re-differentiate them. So what is the point of the passage? Is it necessary?
Well, the point of the passaging is that so if we have 100 cells, we place, okay, if we have 25 cells, we place those 25 cells on a dish, and then we let them expand. They proliferate. They make more cells, right? They proliferate. So now I have 100 cells and fill up my dish. I take those cells and I split them in 4 parts of 25 each, and I plate them again on the surface, and I let them expand. Each one of these cycles is called, passage. So the more you do that, it seems, those cells lose something. Lose their ability to make cartilage.
I want to thank Dr. Athanasiou for a marvelous talk, concise, accessible, hopeful in the way, engineering brings us such marvelous optimism for the future. And let's face it, how frequently do you hear engineering talks that start and end with Sophocles? This was grand. So on behalf of all of us who have joints that are rapidly approaching the point that we're going to be in need of the products that I think will come out of this research, we're very grateful. And I'm grateful to all of you for coming. We have a reception out in the foyer here. And on behalf of Scientia, of which I am director, I neglected to point that out at the beginning, I also invite you to come and join us in the next year when our topic is going to be memory. It's going to be, I think, very exciting. We will have as the Bachner lecturer Dr. Eric Kandel, who won the Nobel Prize in 2000. So please.
This program is protected by copyright and may not be redistributed in whole or in part without the express written consent of Rice University Digital Media Services.